This is a step-up difficulty. This is a problem from the Hibbler textbook. It's basically an A-shaped frame extending out from a wall. There's no pulley. There's no cable. My question to you is this member a two-force member? You want to say it is because you're used to seeing a strut like that. But because this strut extends beyond B and has a force applied to it here, it's a three-force member. So there's a reaction here at D, there's a reaction here at B, and then you have a force applied here. So there's no two-force member here. For the purpose of this problem, we want to analyze the entire frame. If this was an exam question, you would just be asked to deal with a single member, which we'll talk about here later. But for a homework problem, you're typically asked to find all of the reactions. So what do we mean by that? So basically you have the entire frame, and you've got an EX, this is a pin, and this is a roller. And you've got an EX and an EY at the pin, and then you have an AX at the roller. So there's three reactions on the overall frame. And then there's reactions at the individual pins, that are internal to the frame. So if you count the total reactions that you're looking for, you've got EX, EY, and AX. Those are three. You have DX and DY at this intersection, BX and BY, and CX and CY. So you have 6, 7, 8, 9 unknowns for this frame. So remember, in rigid body equilibrium, I can write up to 3 equations per member or per body. So for a frame made up of multi-force members, I can write up to 3 equations for the overall frame, and then I can write up to 3 equilibrium equations for each piece of the frame. So somehow I'm going to have to write a total of 9 equations to get these 9 unknowns. Often, a very useful first step is to deal with the overall frame first. And often that will unlock the rest of the problem. So let's just deal with the overall frame first. So to draw the free body diagram of the overall frame, you don't need to include all the details. So let me just do that on this piece of paper. So basically you can just draw a basic triangle like this, none of the details. I can draw an EX, an EY, an AX. There's basically this point here hanging down with a 300 Newton load there. And I have this point here with a 600 Newton load. And this is 2 meters, 2 meters, 1.5 meters, and 1.5 meters. So 3 meters total. 4 meters total, and then this guy coming down here is 1.5 meters. So this is my free body diagram. I've not put any details of the interior of this frame. All I need is just the basic external envelope of this frame. And so it's pretty straightforward. So what's EY? If you just mentally sum forces in the Y direction, this is 600 down. So EY is 600 newtons up. That's easy. For EX and AX, if you sum moments about E, well, we'll come back to that. So that's how the free body diagrams work. Just keep it simple. Just draw the overall envelope. Be sure you get the dimensions right. And so if we sum moments about E, I basically have 600 times 4 plus 300 times 3 plus 1.5, so that's 4.5, minus AX times 3. And we get AX is 1250 newtons there. Once you get AX, then you can sum forces in the X direction. If we take to the right to be positive, we have AX minus 300 minus EX is equal to 0, and you can solve for EX is 950. So often, the free body of the entire frame is a useful free body. Now, on an exam, it's slightly different. On an exam question where there's just one unknown you're looking for, it's a little bit different, but we'll talk about that a little bit later. But for a general homework problem, a general frame problem, the overall frame is an important first step. So I've drawn 3 equations now, and I've got 3 unknowns, and I wrote those for the entire frame. Now we're going to take the frame apart. Remember, for trusses, one of our key steps was to expose internal loads. We took the truss apart. We looked at a joint, we looked at a section, but to do that, we had to break the truss apart. And that's what we're going to do here. So we're going to break him apart into a member EDC, a member DB here, and then the horizontal guy, which is A, B, and C. When you take this guy apart, this is super critical. We already found EX and EY, so we can put them on here. EX is 950, EY is 600. We already found AX. AX is 1250. Looks like that. When we took this guy apart, it exposed the pin reactions at D. And so there's pin reactions on the diagonal member at D, and there's pin reactions at the top of this vertical guy at D. And this is super critical. You have to draw these equal and opposite one another. Equal and opposite. Because these pin reactions on the diagonal are those exerted by this guy onto him. But then this guy exerts the equal and opposite reactions on this guy. So you have to draw them equal and opposite, or you're going to mess yourself up. Same at C. So at C, I've got the CX and CY here, and I've got the CX and CY here, and they're equal and opposite. And the same at B, BX and BY. BX and BY, they're equal and opposite. One is the action of the one member B onto A, and the other is the action of the equal and opposite action of A onto B. You have to do that. You have to know how to do that. So if I inspect these members now, I've got these guys. One of the things that you see here, if you look at this horizontal member right here, so AY is 0. So there's a roller here, so AY is 0. If AY is 0, if you come down and take a moment around C, the only force in that moment equation is BY. There's no AY, there's no other force. And so BY has to be 0. And that's this guy here. Furthermore, if you sum moments about B, there's no AY, there's no other force. So CY has to be 0. So once you get those guys from ABC, then basically the CY up here is 0, and then the BY here is 0. Once you get BY equal to 0 here, if you sum forces in the vertical direction, if BY is now 0, there's no other force with a vertical component, and so now DY is 0. Okay? And so this guy is 0. Finally, if we come to, so this is member DB. This is member EDC. And this is member ABC. I like to, when I take apart a frame, I like to keep the pieces kind of in close to one another, so I have the visual cues of seeing, okay, these guys are equal and opposite, these are equal and opposite, and so I keep them reasonably together. And then when you write equations, write down which free body diagram you're referring to as you write these equations. So here I said overall frame, and I wrote the equations for the overall frame. Here, these equations are based on ABC, which we saw. So now we're on DB, and again, since BY is 0, which we found from here, if we sum forces in the y direction, dy is 0. Finally, we can sum moments about D to get Bx. If you sum moments about D and take clockwise to be positive, I have 300 times 3 plus Bx times 1.5 is equal to 0. So I get Bx is equal to negative 600 Newton as drawn. This is something I like to do. So when I'm working a problem and when you draw the free body diagram, you assume a force and you assume its direction. When you calculate that number and it comes out negative, what I like to do is I like to say minus 600 Newton as drawn, which basically says that the way it was drawn, it really acts opposite of the way it's drawn. But don't go up here and change the free body diagram. Leave it as is. And then when you sum, so once you get Bx is minus 600, then if you sum forces in the x direction, we get, so Bx really acts this way. So A dB really looks like this. This is dB. And so you have 300 here for our applied force. We get Bx is really x this way. And then you actually discover the dx this way, which is what I put there. And this makes sense. So this dB now is an x equilibrium. So if you sum forces in the x direction, 600 this way and 600, so it's an x equilibrium. And if you sum moments about B, you have 300 times 1.5 one way, and the 300 times 1.5 the other. So this guy balances in moment balance as well. So dx is equal to 300, the way I drew it. And this is 300, but Bx is just the opposite. Finally, when you get to ABC, we already found By is 0. We already found Cy is 0. We just found Bx is equal to 600. Actually, in this direction, Bx is negative 600. And so, based on the free body diagram, if I take to the right to be positive, I have Ax plus Bx minus Cx is equal to 0. I plug in 1250 for Ax. I plug in minus 600 for Bx. And I go minus Cx here is equal to 0. And I get Cx is equal to 650 newtons in the direction that is shown. Basically in this direction here. And so basically we've now found all 9 forces. And we wrote a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 equations in the process of doing that. And actually, solving for a frame is a lot of fun. I mean, you draw the overall free body, you draw the free body diagram of each piece, and then you just start assembling. You can get some unknowns from one piece, some unknowns from another piece, and then just start piecing it together until you have everything. And so this is a classic frame, and it's a good example of of how a frame works. And some of the skills that you have to have, drawing forces, equal and opposite. And keep in mind, do not draw pin reactions at D or at B or at C without taking him apart. You have to take, it's once you take it apart that you see the forces. It's like with the truss. It's like as long as the truss was together, there was no forces. But you had to cut the truss apart. You had to cut away a joint or cut away a section. Once you cut it, then these internal forces appeared. And so if you just start drawing pin reactions at this guy, it's like, are those the reactions on the diagonal? Or are those the reactions on the vertical? Because they're equal and opposite. And you will confuse yourself and you'll get it wrong. And the goal is to get it right, not wrong. And so don't draw forces on this guy. Once you take it apart, then draw one direction at D here, and then the opposite direction on this D here. And the same is true with every pin. So this is a classic. This is just a classic frame. And so these are the final pictures here of our reactions. And so I've got the EX and EY that we found, the DX, the CX and CY. Oh, one more thing I didn't say was, so what do we do with this force here, this 600? And so as long as the frame is together, you have the 600 hanging there. But once you take it apart, what do? Do you put the 600 on the diagonal, or do you put the 600 on this guy? And the answer to that question is you can put it on either or. Just don't put it on both. So just choose. Either put it on this guy or put it here. But don't put them on both. Because really, keep in mind, this 600 Newton force doesn't hang from this member or from this member. This 600 Newton force hangs from a pin. There's actually a pin that inserts through this hole here and through this hole here, and the 600 Newton force hangs from that pin. So it doesn't hang directly from this guy or this guy. And so the CX and CY are the reactions between the member and the pin. And so by leaving the 600 here basically means I left the pin in this member. If I put the 600 here, then that would be that I left the pin in this member and not in this guy. So you can do it. So first of all, again, the overall frame, the 600 has to be there. Once you take it apart, leave the pin in this member or leave the pin in this member. And the problem works exactly the same way. But physically, that's what you're doing, is you have the issue with the pin there.